I'm going to talk on behalf. I'm going to talk on behalf of a bunch of people. Some are listed here. There's actually a much larger cast of characters involved. And the other thing is, what we are presenting is a work in progress, but it's actually, I think, something that is should be fairly interesting to a larger community. It's an example of the kinds of things that we are working on and devices we are building will help and accelerate. And it's interesting, like, while I was thinking about how to start today, I was listening to the keynote from 2 days ago, and the topics were the breakdown between hardware and software. How is congestion control going to grow and evolve, because that's an evolving or continuously changing landscape and is continuously getting bombarded with newer and newer problems, and therefore the solutions have to adapt over time. And finally, ChatGPT is everywhere. Accelerators are taking over the universe, and it has fundamentally changed the way communication patterns are going to evolve, and also what the loads and requirements out of communication are going to look like. So in the free time that we have, I wanted to make sure that people understood that that's what we want to really talk about. The specific talk is going to address a very sort of narrow sliver through that space. And that was too quick. We still have 3 minutes to kill.
I think that's all right, because you're right up against the break. So if you end a couple minutes early, it's okay. We can just break a couple minutes early.
Okay, so then let's just go. Okay, so we're going to talk about RDMA and Linux TCP, and in the course of this talk, you'll understand specifically what we mean by that. So a question that some of you here have actually grappled with in the past and should be wondering, why are you asking this question again, is why look at RDMA and TCP? Rocky and IB have solved most of the problems that most of the high-performance communication requirements have imposed. There's obviously a lot of work still to be done. Most of it is around enabling out-of-order delivery, enabling selective acknowledgement, thus improving the efficiency of retransmission, and enabling something better than what is currently existing as the congestion control mechanisms. There were some talks also earlier today talking about similar enhancements. But this is an area of profound interest, because many different workloads and many different workflows have very many different requirements out of the congestion control schemes. So that's the area where Rocky is sort of growing. The other thing that is seen is that as you transition from specific custom-built networks, which are built around RDMA, to trying to make the applications be more general purpose, mixed-use traffic becomes a much more important factor. There is familiarity around TCP, there's familiarity around debugging problems at scale, understanding how issues are handled, how bandwidth is apportioned, how fairness is treated, and so on and so forth, which are things that TCP brings to the table and forces us to look at it again. And lastly, which is sort of the same point, Rocky today typically runs on custom-built backend networks, or some custom-built, purpose-built networks, I should say. But if you were to build such an ecosystem, you have to do something for general-purpose storage. The previous talk was talking about cloud services. Cloud services are almost always running on some variant of TCP. And then, as we are seeing more and more of machine learning's growth, we are seeing inference, which is the serving part, which is specifically or typically the cloud path, which is not running on these custom networks, but still now are exposed to these very large data and bandwidth demands. So the question is there something fundamentally wrong with TCP, and does it all need to be overhauled, or can we reuse it? Clearly, there are many opinions in this space. There are people who say TCP is wrong for the data center and we need to do it all over again, HOMA being an example of that. But let's see what we can do for it. So why look at TCP? What are in TCP's corner? The most important part would be the congestion control algorithm richness. This is an area that has been actively researched for decades now. There are many behavioral models, and you can pick one that works for the use case that you're looking for. Are you looking for very short data center type links? Are you looking for very long WAN type links? If you're looking for mix, you can pick, right? There's a large collection of options available. Congestion control, rate control, fairness is very well understood. Selective acknowledgement and efficient retransmission also has been very heavily researched. And TCP, by definition, supports out-of-order packet delivery with in-order completion. That's sort of part of the DNA of the system. So a question that is worth asking is, hasn't this been tried before? Clearly, iWarp was one of the bigger attempts at this, where an attempt was made to put the RDMA framing concepts on top of a TCP-based retransmission scheme. The way it had to be implemented, at least in the time in which it was attempted, it had to be implemented with a hardware TCP engine, which by definition actually ruled out most of point number one. You had to pick certain set of things that you could implement, whether it's firmware or it's hardware. And it ended up basically limiting the rate and the speed and the flexibility of TCP that you had available. In addition, the framing conversion between trying to do TCP on the wire and RDMA to the host ended up making that protocol extremely complex and very difficult to realize. Another attempt was a stack called Open Onload or Onload. Solarflare did it. Turns out I actually implemented a similar stack at a company called Precision IO, which was putting TCP libraries into user space and then plumbing the path through such that instead of doing locked contended TCP execution per application thread, you executed it as a library in the application's context. The Solarflare solution was fairly successful, I would say, in the HFT HPC space. I'm sure people here have used it. But it also suffers from the same kind of problem, which is it has, over the years, diverged from what you would call the standard TCP, which arguably is the Linux implementation. And what that has led to is that certain enhancements and improvements that the Linux stack has experienced is not available in that model. Plus, over time, it became a divergent solution, which led to some more friction, let's say. And then there's DPDK, standard classic user space TCP implementations, often used in a lot of middle boxes. It's very popular in telco solutions where you're trying to do TCP with the least CPU overhead and least compliance or compatibility requirements. It's, I would say, a bit boutique and again, not often seen as a general purpose, widely deployed solution. So the question that still remains is, can we make TCP easy to implement on simple hardware and get the performance we need? So now on the negative column, what's held TCP back over the years? Sockets, right? I mean, there's hopefully not much of a question on that front. The synchronous in-order, inline, syscall-based sockets interface is problematic. It doesn't fit in with the modern asynchronous, low overhead sender-receiver type models. However, the install base is so large that actually deprecating sockets, I think, is not an exercise that is worth achieving in the near term. But an additional set of problems, messaging, which is an access pattern that is quite popular, implementing that on top of TCP is actually reasonably hard. And specifically because the message framing on top of a byte stream sequence is a non-trivial problem to solve. In addition, if you want to allow out-of-order message delivery, that gets extremely hard. Clearly, upper level, there are existence proofs, right? NVMe TCP exists, but you need to do a lot of work to extract the PDU stream out of the byte stream and make sure that each of the layers work independently and correctly over time. And that means that the efficiency and high performance path of it is not trivial. As in fact, the previous talk was talking about, you actually have to do PDU framing in some staging buffer and then do your DMAs. And traditionally, TCP has not had the ability to do zero copy. We'll see later with some data about the impact of zero copy. This has obviously been changed in the recent past. The Linux implementation has a fairly good TX zero copy implementation. The RX has its own issues. And the TX, while it is great and it is truly zero copy, it's not as efficient as an RDMA send or a write operation. And one of the problems with the kernel page flipping mechanisms is that it doesn't work very well with heterogeneous memory unless the CPU has complete control over the actual page tables that refer to the heterogeneous memory, which could be in some PCI switch and not under the host MMU's control. And lastly, one of the issues that TCP has run into is this, what I call precise placement and management of buffers. While obviously you can alloc a buffer and use it for read and write in a TCP socket interface, if you want to do something more specific, where you don't want the overhead of SKVs, you don't want the overhead of any additional data that gets allocated from a memory space that you have no control over, it's non-trivial to implement that transparently up to the application. So these are the things that I would say are on the negative column for TCP. For the rest of the talk, we'll try to see if we can solve them, and we'll talk about a particular implementation where we went and tried to attempt to solve this problem. And I should say with successful results. So the test or the ecosystem that we are playing in is this picture on the left. It's a standard Ryzen motherboard. It's got plugged into it an FPGA card. That FPGA card has 2 GPUs plugged into it. And this FPGA card is effectively acting like a network router and a PCI switch at the same time. The speeds and feeds are there. The PCI lanes are all Gen 3 by 16s. The Ethernet ports are 100 gig ports. This sort of is not really relevant. One of the problems with this design and a characteristic of the design is that one of the paths, the right path, the path from the GPU out, is actually not even 100 gig capable. We could only make it run at around 40 gig. So we won't really talk much about that path. And this particular FPGA setup is, let's call it a hardware approximation of the design that we are actually building at Enfabrica. And it supports a couple of interesting features. One is it does full hardware classification and steering, so it can look all the way up to an L5 header. It tracks, once it knows what, specifically at the L4 level, if it knows what a flow is, it can keep track of the byte offset that it has seen inside that flow, and it implements a fairly efficient TSO-GSO scheme. Sorry, I should have said GSO-GRO scheme. That's a bug in the slide. We'll fix it. So this is some data. Let's start with that, and then we'll come back to what it actually means. So the graph on the right is showing you the performance that we could drive using that hardware that we saw, which clearly could not hit 800 gig. So what this experiment did was we basically removed all data, all payload bytes from the packet, so it's running in header-only mode. And we ran an application as fast as we could and the stack as fast as we could. This is an unmodified Linux kernel with our driver running on it, and tried to measure how fast we could run the packet rate such that using 4K MTU packets, oh no, this is actually got variable MTU, sorry, for a variety of MTU packets, what effective throughput we would get, where throughput is computed as packet rate multiplied by MTU size. And what you see, what is very obvious from the graph, is that without GRO, the performance is pretty sad. With software GRO, it's significantly better than the baseline, but it's still pretty low. Using our hardware GRO scheme and our modified driver with fairly low overhead, we can actually come close to hitting that 800 gig packet. The packet rate needed to hit 800 gig over a very large swath of MTUs. And at the lower MTU sizes, our climb rate is also fairly respectable. So it's actually possible to just run the stack at the speed that you want. And that's the statement. One of the things, or the things we learned, like we surmised earlier, the syscall socket API interface is quite problematic. It adds almost all of the overhead. The driver implementation and resource efficiency, caching rather than allocating in the hot path as an example, was very important. The native SAC and ACK manipulation actually worked very well. It kept the rate pretty consistent. And it really benefits from this out-of-order data and in-order completion model. So if there is slight hiccups, it recovers quite seamlessly with no real issues, as long as the hiccups and the retransmissions are within a certain window. Another thing to think about, right? So if you think about the Linux stack itself, it's one of the most, let's say, maintained stacks out there. There are about 5 to 10 commits, of which 1 to 2 that often have pretty significant performance advantages every month. There's a very large community. It's very actively looked at, and people pay a lot of attention these days to the performance and the implications of performance. There has been tremendous amount of improvements to congestion control algorithms. Newer ones like BBR have been pretty impactful in the places where it matters. The short queue implementation has made it such that buffer bloat doesn't become a thing, even when you're using TSO, GSO type schemes. Flowlet routing, which is very important from a link loading and link or sort of distributing data over links problem, which again, in the context of machine learning and these big data type applications becomes very important, because if you have 200 gig links and for a short period of time, all your traffic ends up being on one of those 2 links, you have a problem. Your efficiency overall drops pretty dramatically. There's, again, using eBPF as a configurable intercept, very efficient and very interesting dynamic congestion control mechanisms have been added. And big TCP is a thing that addressed, actually, I should have mentioned this earlier. One of the places where TCP hasn't done as well is effective payload size. And big TCP addresses that by moving past that 16-bit payload size limitation and allowing the hosts to express much larger buffers than something that can be expressed in 16 bits. And the 3 dots at the end to say that there's more coming. So the one thing that isn't in this graph is CPU utilization, which is clearly the key problem, right? Like any other stack out there, one of the problems is how much CPU does it take to be able to achieve the performance levels that you want. And we'll address some of that today. But for people who are really interested in the answers to those questions, I would recommend following those 2 links, which should be there in the slides when we post them. David Ahern gave those 2 talks, and they're actually very detailed about some of the things that we've been looking at and understanding the impact of how these small changes, and in some cases big changes, affect the CPU utilization and our ability to hit these high packet rates. We did look at solutions like IOU-ring and AFXDP. IOU-ring is obviously got a lot of momentum, has lots of very desirable characteristics. It gives you that asynchronous direct access interface that people want. But it's a new API. Its insertion into existing stacks like machine learning is, it's going to take time. Maybe it'll get there. And the zero copy RX path is still a work in progress. And there is a fair amount of work to be done to do zero copy RX efficiently and to get the results that you need. AFXDP, we sort of mostly looked at and stepped over because the primary goal of AFXDP is to get packets into user space quickly. The protocol stack is still a problem that needs to be solved. So it's closer to the DPDK solutions that I talked about earlier, but you don't actually get a battle-hardened interoperable stack that operates at high efficiency as a result. So what did we build? The way we built it looks like this rather complicated picture on the right-hand side. And if you see, can I do this? Yeah, hopefully the laser pointer works. If you look at this picture, the gray bits are things that exist in the Linux stack today. They're mostly unmodified by us. There may be small changes, but nothing that is significant. This thing down here is what we call our core device driver. It's a thing that drives queues, does housekeeping, does all the things we needed to do. And we added what looks like a fairly standard InfiniBand provider and driver library or driver layer into the stack. The picture should be actually fairly similar to any other picture that you've seen, where you have regions up in user space, you have some work queues and completion queues on which you send and receive work. You have a submission queue on which buffers can be posted directly to hardware. The big thing that is different here are these two arrows, where effectively what we do is on the send path, we collect the scatter-gather list and we submit it inside the kernel to the TCP stack and allow it to drive the networking driver to push transmit packets or read request packets out. And on the receive path, we do the exact same thing. When a packet comes in, we go through this library or this stack and then put the data into receive queues, and the buffers where the data is going to actually land, where the actual packet data is going to land, is already available to the hardware, so the data lands in the memory region where the buffer lives directly. So this effectively is a hybrid of sort of the TCP implementation that you see out of the box. But the interesting thing is there isn't a single element in this picture that we've created that didn't already exist. It's really a reformulation and a rewiring of schemes and components that exist in the Linux stack today. So continuing, how does that look on our system? The model we went with is that same picture, right? So now you have your machine learning application. It's speaking through NCL to an IB verb stack. The queues, the work queues, the send and receive queues are available to that application that's going through the driver to a kernel implementation running on that CPU. The payload is over here. You'll see later, we have data for how it sort of compares with the memory region being on the GPU versus the memory region being on the CPU's memory as well. And as we said, the submission queue goes directly into the hardware. The send and receive work queue requests go through the kernel driver that gets converted into our hardware queue format, and then subsequent action gets taken. The one thing worth mentioning here is that the data path, specifically this call into the TCP/IP stack, bypasses a significant amount of, let's call it, functional additions in the kernel stack over the last few years, i.e. all of the hooks that people have been using and adding to sort of hijack or take over data movement. We've bypassed all of that. We've been very selective about which kernel functions we are calling. And it turns out that the Linux stack was always built around a callback style design. So many of the things can actually be isolated and called in isolation rather than taking the whole enchilada from the top of the socket to the bottom of the port, and vice versa. And while this block here says TCP/IP, the other thing worth noting is this could be anything, right? So we won't talk about it today, but the structural model that we are talking about allows us to replace this block with RxC, which is a Rocky implementation in the Linux kernel, and most of the rest of the talk would remain the same. So we talked about this earlier. One of the problems with trying to solve this or trying to build this is the inability or the inefficiency when you try to put messages on top of a TCP byte stream. The big attempt to do that in the past was this thing called iWarp, which was to layer the RDMA stack on top of TCP by using this RDMA-P over DDP over MPA scheme, such that you could get the markers in the right places and you could do zero copy direct data placement. The other option, this was basically an L5 protocol, and you had to build fairly sophisticated hardware that could go pull these things out. One of the things we are adding, or our implementation has added, is this notion of what we call messaging over TCP. And the way we are doing it is by adding a little TCP option header. I call it BTH-like. It's an information header. It's all the things that the BTH, let's say it lives in the same spot that the BTH header lives in a standard Rocky packet, because and allows us to build correlations between messages and queues and where that message needs to be delivered. And specifically, it carries two fields of information, not 2 bits. It's significantly more bits. It tells us the phase of the operation. We are just using the Rocky opcode. It tells us which message this particular set of bytes belong to, and it tells us which byte offset corresponds to the start of this message. By using this scheme, it's a bit like the MPA header, or it solves a bit like what the MPA header solves, but it allows us, and it allows our hardware to say, pick a buffer based on this message sequence in addition to the byte sequence, and do the right thing rather than get confused about messaging when it is overlaid on top of a byte stream. This allows us to build, the reason why we believe this is a better way to try to approach the problem than iWarp is because it allows the hardware to stay extremely simple. It allows basic TCP to just work, and when this header shows up, we can enhance it and do slightly more sophisticated things, and the resultant efficiency gains are actually quite visible. The one downside of this is, as stated here, that we are adding this currently as a TCP option header, which means middle boxes will not be able to do the right thing. But for the data center use case that we are currently focused on, we don't see that as a problem. And if people want to collaborate with us to get it into something that looks like a spec and a standard, such that middle boxes can work with it, that's something we would be very interested in doing. So what's the point of having a talk if you don't have data? Here's some data, and I see we have 6 minutes left, so I'll try to speed up a little bit. Before you look at the graphs, I should state that this baseline system, that FPGA system that we were showing, at a baseline, if you just run TCP and like iPerf on top of it, we get like, it's at 4K MTU, or 4K message size, I should say. That's a bit of a mistake as well. We were getting hundreds of microseconds of latency, but this system is capable of hitting the 3 million packets per second you need at 4K MTU, such that you could fill the 100 gig pipe. So keeping that as a background, to stare at these graphs a little bit more, the left one is talking about how we compare against a standard Rocky, I think it was a Mellanox 5, a CX5, doing CPU to CPU transfers or CPU to GPU transfers. This is GPU direct for people who are familiar with that, where the destination buffer is coming from GPU memory. And you can see the latency is clearly not at the same level as the in-production hardware-based implementation. There are 2 reasons for that. There's a fair amount of work left for us to do in terms of improving this efficiency in the software side, but also the hardware is running at like a quarter of the clock rate that we need, and it's missing a bunch of optimization. So many of our transactions actually require multiple DMA cycles before you can get to where you need to get to. But what is still, I think, impressive is as you start looking at the 4K and 16K numbers, you'll see that our latency is still fairly flat and solid over those ranges, which is not what you would see if you were running standard TCP over similar ranges. Maybe the more interesting side is the throughput side. Here also, if you notice that, let's start with the negative first. At 4K, we are significantly worse than where the Rocky NIC would end up. And this also right now is a software and tuning implication, because we know that we can hit that 100 gig number when running standard TCP. So this is actually a problem on our IB stack. But the more interesting part is that we manage the curve, we hit the throughputs, and if you look at the 16K, 64K size, which is where most of the effort around machine learning is focused at, we are just fine even with the stack that we have right now. The other thing I should point out is that our path to the GPU, because it's going through again our solution, is a little bit lower in performance than the rest. And the last graph I'll show you is this. And this is one of the points that we're trying to make here, which is by doing what we've done, where we've effectively isolated the stack from the rest of the application and the memory that is servicing these operations, in our case, the GPU, the thing that you see is that you're actually going to get better TCP performance. And let me explain what I mean by that. So the red and the blue graphs here are showing, again, standard CPU to CPU and CPU to GPU operation. The yellow and the cyan are showing what happens to those two curves when there's a memory aggressor in the mix. So what we did is on the system, actually Raghu did this, we ran stress NG, and we sort of maxed out the DRAM access in the background. And what you see is that the CPU to CPU path starts suffering hiccups, has sometimes horrible side effects. Whereas the CPU to GPU path, because the GPU memory controller is not actually getting swamped by stress NG, is able to more or less keep its performance. The blue and the yellow are slightly shifted, but the peaks remain exactly where you expect them to be. So the isolation model not only works, the isolation model actually addresses some of the performance, let's say, accusations that are made against TCP. So in summary, get the OS out of the way, apply RDMA as an application interface on top of the Linux TCP stack, and your performance will show pretty significant gains. We are almost out of time, so I'm going to rush through these slides, and I saw some questions fly by. Maybe we'll get to that. And I'll actually ask David and Roland, since you're around, to maybe unmute and take questions if any come our way. Okay, I will read some questions out maybe. Is this correct that this can support, from Sean FT, that this can support RDMA read-write flows? What's the max message size you can support? David, Roland, do you guys want to take this?
So, yeah, I mean, it is correct that we can do RDMA operations. The BTH header that you showed, Shrijeet, we have an opcode in there, and so we can steer pretty easily in hardware to different processing contexts or whatever to handle RDMA. And then, yeah, right now we have a 24-bit message size in that header. Seemed like a good trade-off for various implementation reasons, that going up to that sort of multi-megabyte message size, you're not going to be bottlenecked on message rate, even at 800 gig and terabit type throughputs, but it doesn't add a lot of complexity around having to go backwards very far in time for retries or things like that. So that was the trade-off that we took.
And also some of the limitations are also this particular FPGA approximation of our hardware. There are things that our device does a little bit better. A question from Peter Goetzman. With the libc control path plus IBverbs data path, does the application need to make special steps to allocate and pin buffers? I'm curious how much application needs to change. The high-level answer, Peter, is if it's an RDMA app, it'll just work. There is no additional changes that you need to make. If you're trying to do some kind of application level hybrid, then I would recommend you use the RDMA mechanism to do the pinning, do the registration through the word registration call, and then proceed at will or as you need to. By the way, I'm just going to keep moving. If you guys don't like the answer or have a follow-up question, please jump in. I think this is more of a comment from Bernard. Did you look at soft IWARP? It exemplifies your claim on PDU parsing complexity, but shows rather decent performance if segmentation offloading is used. I agree, Bernard. I think so what we saw, and I mean, we've spent a lot of time looking at what it means from a NVMe TCP perspective, as an example. There are some things we can help. Hardware helps with segmentation and segmentation signaling, so to say. But the problem with all of these upper level PDU type schemes is that the worst case is quite bad. Like if you end up in a retransmit on a PDU boundary that was half done and spanned a bunch of messages, it's very messy.
I agree.
Yeah, and actually, this was I'm glad this question was asked because I wanted to make a comment in that direction also, which is that it is true, like you said, that there are ways to handle PDU-based protocols, but there is sort of a fundamental difference, which is if you need to look inside the TCP stream to find PDU boundaries, then you need to, sort of fundamentally look at the full payloads of TCP, which just is more expensive and less amenable to stateless offloading than a scheme where the packet boundaries that you see on the wire are aligned with the message boundaries.
Right.
It means that because you get the packet boundaries, it means you only have to touch the headers as they fly past, and the payload can be sort of much more zero copy, and like Shrijeet mentioned, go directly to a GPU or something like that.
Yeah, and let me ask you also, if you are implementing IWARP, especially in software, you have to deal with the trailers checksum, right? So you give a trailing element after the data, which is even worse. Yeah.
But Bernard, you obviously have track marks from attempting to implement this somewhere, because that's actually one of the
so it's upstream Linux. It's called SIW, soft IWARP.
Mm-hmm.
Yeah, we looked at that, and we actually looked at implementing or accelerating that quite a bit. And like the checksum ICRC combo question is actually far harder than you might think when you're trying to build a very high bandwidth, very high throughput device.
But you would face the same problem if you would add a CRC to your stack, right?
Maybe. We can talk about it offline.
Okay.
Okay, and I see one more question from Sean in the chat, following up on the RDMA, that there's not an R key in that header. Yeah, so we didn't put the full structure there, and the idea would be that so in Rocky, the R key is not in the BTH, it's in the extension header that follows the BTH. And so essentially we do the same thing where if the opcode in the TCP BTH says that there is an extension header following it for an RDMA operation, then you would look there for any memory keys or whatever else. We haven't looked at, let's say, atomic operations, but you could, in theory, I don't want to go too far out over my skis, but yeah, in theory, you could have an atomic extension header there also, or, anything analogous to what Rocky and InfiniBand do.
Yeah, so the sentence I would leave that with is, Sean, we are looking for participation or collaboration on exactly what that header needs to be. Now that header, I think your specific question around the R key leads to the what else should we put in there? And putting too much has problems. The TCP option header has size limitations and implications of expansion. So yeah, if you guys are willing, yeah, if we should continue this conversation offline is the high order bit. Okay, before the organizers kill me, we are 7 minutes over, though we are eating into the break. We are happy to stay and take questions, but you guys tell us.
This is great. I certainly don't want to stop any discussion. And absolutely, the meeting will remain live, of course, during the break. So anyone wants to continue the conversation is welcome to do so. But for those who need a break, we will be taking a break now, and we'll be reconvening at 10:30 in about 20